The 10th edition of Numerical and Symbolic Abstract Domain Workshop. I'm Vincenzo Arcieri, and I'm super happy to have organized the NSAD workshop with Michele Pasqua there. And this workshop was missing since 4 years. The last edition was in 2020, and me and Michele are super happy to revive NSAD this year. So we got 6 papers, 5 full papers and 1 short paper, and yeah, we feature a keynote speaker by Caterina Urban, and we'll start with her, with the second part, the part 2 of the talk that she had in SAS. And so that's all. I leave the floor to Caterina with her talk. Thank you.
Okay, good. Okay, thanks to the organizer for the invitation. So yes, this is sort of a part 2. So I did a tutorial at SAS on machine learning verification. And here I decided to actually remove the word verification. I will not just talk about verification, but various things where we can basically use abstract domains for machine learning in various ways. Why I started caring about machine learning is mainly, well, because as you know, there's a lot of machine learning being used these days, and a lot of it also is appearing more and more and being used more and more in high-stakes systems. High-stakes is safety critical, but also systems or situations where this kind of software has an impact, I would say, on our socio-economic lives. And there are various reasons for this. So first of all, we can now use machine learning to do things that we couldn't do with explicit programming. You think, well, self-driving cars, image-based taxi in takeoff and landing. Yeah, they are looking at these things in the avionics sector. We can also use machine learning as surrogate models. This was basically what I was looking at in the tutorial. We have reference systems, and we can use machine learning to approximate these systems. And this allows us to basically equip airplanes, for instance, with new functionalities that we didn't have before. And then finally, this socioeconomic impact comes where we can use machine learning to automate decisions in healthcare, finance, hiring, and what's not. So I just talk about machine learning system, machine learning software. For me, in fact, the machine learning software is anywhere that appears in the machine learning development pipeline. So any code that is used for preparing data, for training data, for, well, actually, doing the predictions. So the talk afterwards will talk about this data preparation phase, actually. So that works well because I'm talking mainly about these 2 parts. I will start with the model deployment phase. Touch a bit on training, and the rest, well, Greta will continue afterwards. So it all works out. So I'm starting with the model deployment, and here the main challenge here, so these are the models that are already trained, okay? And the main challenge from a formal methods, formal guarantees point of view is that these are trained optimizing some loss function. So you basically have some probabilistic guarantees, right, on their behavior, but it doesn't give you any formal guarantees on their behavior under all circumstances. So this is where problems come from. In particular, in the machine learning community, this started, but they noticed basically that, I mean, you all know this, that these models are vulnerable to small perturbation of their input that can dramatically change their outcome. And this is actually also the motivation why the formal methods community started looking at this kind of systems. So historically, the formal methods community has worked on traditionally safety critical software. And in the past, I don't know, I would say 10 years or so, we have been looking more and more at machine learning software. So out of curiosity, I looked at the publications on Google Scholar. I took some keywords that are common in the field. And these are, you see the number of papers. So 2024 is not yet finished, but we already have a lot of papers in the pipeline. So this is for us, the formal methods community. But the interest and reaction from the machine learning community is not there. They really do not care about any of this, pretty much. I started asking myself if there is any way to make formal methods interesting or have a dialogue with the machine learning community in some way. And so this keynote basically will cover 3 ways or 3 possible directions in which we can do that. In the first direction, I will stay on verification. So closer to what we are used to. And then I will go a bit further, so into the training, so directly doing machine learning stuff with a touch of formal methods. And then something in between, where we can use formal methods to do something else than verification, which is explainability. And what one thing I didn't say, please, we're a small workshop, ask questions at any point, you don't need to wait until the end. Okay, so verification. So this was a nice collaboration with Fujitsu. They had a nice use case that they needed to solve. And this got me thinking into what kind of verification problems we can do that may be also somehow useful or interesting to the machine learning community to go beyond this local robustness problem that they look into. So essentially, what happened was, yes, most of the community now is doing this robustness verification. What happened to us in this project that we had to do robustness verification, but with a touch of awareness for interpretability concerns. I'll make this more clear, of course, but this is a bit the flavor. So it's not robustness of the classification, really, but it's robustness of the explanations for the classification, in essence. So the problem is this: we had what they had was basically a system that was classifying some metal pieces based on whether they were defective or not. So they had essentially the camera was looking at the pieces, and based on their aspect, they was deciding whether it was an okay piece or defective piece. And what happened was that often they had problems with the like regular perturbations of the light, so modifications in the light of the room. They had sometimes some dust that was covering the objective, so there was what we call patch placement. So basically some part of the image was a bit covered, and sometimes the object was not exactly in the position where they were expecting it. It was just slightly shifted left or right and things like that. So we had some sort of what we call semantic perturbations. And so the idea was identifying safe ranges for the parameters of this perturbation. So when can we trust the classification of the system in case of this perturbation that can happen naturally in this context? And what we realized was that, in fact, if we just look at the classification robustness, this was not enough. We had cases where, I mean, this is with an MNIST image, but we had cases with these metal pieces where just completely changing just the brightness of the image, we couldn't see the metal piece anymore, but it was still classified as an okay piece. So the classification didn't mean anything, in essence. So what got us thinking was that, well, maybe we can have something more meaningful that we can look at that will be a bit more semantically meaningful in terms of robustness. So what we looked at was in the machine learning community, they have a lot of these explainability techniques or ways to explain why some image is classified in some ways. And one of them, I mean, there are more advanced techniques these days, but one of them that has been used a lot are all these gradient-based techniques, where basically you have your image, and based on the magnitude of the gradients, the classification with respect to the inputs, you basically identify the pixels that are more responsible in a way for the classification. So we decided to do that as well with our images. So here it is our 8 image where we just increase the brightness. And you see that at the beginning you can sort of distinguish the H shape, but beyond a certain point, you don't really see the H shape anymore because, well, the brightness of the image is too much in this, and you lose basically the reason for classifying it as an 8, even though the model still classifies as an 8. So there is a sort of, maybe around here. So here we can still sort of see an 8, and here we don't see it anymore. So what we decided to do is basically use this criteria to define a new robustness problem, which was the robustness of the explanations, the saliency map. These are called saliency map or gradient-based explanations, however you want to call them. So what we decided to do was basically say, okay, we have our image and the perturbations that we can apply to this image. So for each of these perturbations, we have a corresponding saliency map and this explanation. We can compute this gradient-based explanation. And then depending on the perturbations, so the brightness change, the patch placement or the translation of the image, we have some sort of expectation on what is the saliency map. So basically we have the original saliency map. We can also apply the transformations to that saliency map. And then we can compute the distance between those, the expected and the actual one that we get. And beyond a certain threshold, then maybe we don't trust. The distance is too much. And so we say that this is inconsistent and we cannot trust this classification anymore beyond this perturbation point. So we can allow this much perturbation of the brightness. Beyond that, we don't trust the model anymore. So I just wanted to give you a bit of a flavor of what kind of analysis we can do with that. And give you, so here, spoiler, there won't be any abstraction yet. So in fact, this is one place where we're missing abstraction still, and it's an opportunity for maybe doing some research in this direction. So I'll give you a small example. This is an image with 4 pixels that is classified as a dog or a cat. Bear with me. So the nodes, we have one single hidden layer with a ReLU activation function, so this max function between the linear combination of the nodes in the previous layer and 0. So this is our image. And you can obviously see that if you do all the calculations, this is obviously a cat. From this image, you can clearly see a cat. I hope nobody disagrees with me. Okay, never mind. So for the classification, with these 4 pixels, we get a cat. The saliency map, as I said, is basically the gradients of this node with respect to the input. So in essence, if you replace, you do the back substitution up to the input, you get the inputs with some coefficients. And these coefficients are basically the importance of the pixels with respect to the classification. So this is the saliency map for this image. So what it says basically is that this pixel here is the most important for deciding whether this is a cat or not. These two are somewhat less important, but equally important, and this is the least important pixel. So now if we do perturbation, we change the brightness of this image. This is the new image that we get. And this is the corresponding saliency map, or the corresponding explanation. So you see that the importance relationship is still somewhat maintained. This is still the least important pixel. This is still the most important one. These are slightly different, but still in between those two, in essence. If we go further, we do further perturbations. We get now that we don't distinguish the importance of these 2 pixels anymore, for instance. So here we are losing some relationships between the pixels, and the distance between them is increasing. So we can say, well, in this case, we can trust this much perturbation of the brightness, not beyond. So yeah, this is how we can say, okay, this is robust, beyond that is not. So how can we verify this robustness thing? So in the project, what we did, we actually leveraged this other work. Basically, it's a way to encode the perturbations directly as layers of the network. This way, you basically end up with instead of having the image and considering all possible perturbations of the image, you basically have the parameters of your perturbation as input, and then the network basically encodes all possibilities of perturbation of the input image. So in the example, basically, if we consider just brightness perturbations, this means we add the parameter to the network. We end up having the image as the bias values, basically, of the nodes, and we add these edges. Okay, so then I have to check the time to not go too long on this, but okay. Okay, so then we end up with this network, and we basically want to find the ranges, or which range of this input space we can trust the classification or not. So we have this robustness of the explanation. So what we did was actually leverage the disactivation patterns of the ReLU. So the ReLU function is this piecewise linear function here. So in the whenever the input, the node is active, so it's is positive, this behaves as the identity function. So we say this is active, the ReLU is active. Whenever the input is negative, the ReLU is inactive, and so the value is 0. So in essence, you can consider it as a filter. Basically, it receives a signal, a value, 0, and it's active when the signal continues, as it is, inactive when the signal is killed and reset to 0. So I will use 1 to identify the active state of a ReLU, and 0 for the inactive state. So when I do the verification, okay, I will leverage these activation patterns to basically explore the input space. You'll see it's a very somewhat naive analysis for now, because there are no abstractions. So basically I start with my input image. So basically the parameter is 0, I have no perturbation. So the input image is my original image. And now I check what is the status with this input of my ReLUs. So in this case, they are all active. So that means that basically for all nodes, I pass the function as it is, or the value as it is. But in particular, what this pattern gives me is also constraints on the input space. So it's not just the single image, the original image that has this pattern, but other images in the same region of the input space. So in particular, when I say that all of these are active, this means that basically if I take their value, so their value is the linear combination of the nodes in the previous layer, this is always positive. Same for here, same here. Same for these nodes, right? These are the value of this node depends on the input plus the bias. This is all positive, greater or equal than 0, greater or equal than 0, all of them. When I put all of these constraints together, this basically identifies this region of the input space. So basically for all input parameters that have values between 0 and this 1/14th, they all share the same activation pattern. So basically I can do the analysis for this region of the input space, considering that all these ReLUs are always active. So we do classification robustness for now, and then I'll do the saliency map. So for the classification, this means that basically, okay, I start with this input space. They're all active, so I can do some sort of symbolic propagation. So I'm saying, okay, this is active, so it's the identity, so it remains the same. I do this linear transformation and so on. So this gives me basically expressions for these two nodes that depend on the input. And now what I want is a classification robustness. So what I want is that I always get a cut, so that this value is always greater than this value, which is here. And in this particular input space where I started the analysis, this is true. So here I have classification robustness. Okay, now let's do this saliency map robustness. So here, in essence, is the same, right? I can do the propagation as before. I do the backward propagation to get the gradients, leveraging still the activation patterns. For each activation pattern, since the ReLUs are fixed, basically it's the gradients are always constants, it's just coefficients. And in particular, the saliency map is really the same as the one of the original image. So the distance is 0, so we do have robustness there. Now, how do we explore the rest of the domain? We can do a naive search. So basically, we have our initial region of the input space. Here I have basically 2 parameters of perturbation, just to give you an idea on how we would do it. And then basically what we can try to do is basically find the adjacent activation patterns, and then see for each of them whether we have the robustness or not. So how we go about that? Well, we just flip the activation status of a ReLU. This will give us another region of the input space, this one here. And then this will give us other output constraints. We can do the same check there, and this is still robust for the classification. Similarly for the saliency map. Again, we have fixed all the ReLUs, so the saliency map is constant. The coefficients are constants. So we can just compute the distance with the original one, and this is below our threshold of distance 4. So we're all good. And then we can continue like this, right? We can flip and discover new parts of the input space until we cover the entire input space. So you see the difference between the classification robustness and the saliency map robustness. For the classification, we can trust perturbations of this brightness up to 0.5. But if we look at the stability or the robustness of these explanations, the saliency map, we can only go up to 0.25. So it's more strict. Then, of course, it depends on your distance, of course. Then you can imagine that this is just too much. You cannot do this on a larger scale network. There are just too many activation patterns to explore all of them. This was a rather small network, and we had just 2 input parameters, and we had all these many regions to explore. It was just not possible. So what we ended up doing in this work was do some sort of under-approximation. So we did some search, what we called it geometric boundary search. So basically we were trying to go as far as possible from the original image. This is the original image, and these are the perturbations that we can apply to it. We try to go as far as possible from it until we find what we call the boundary. So here is the classification boundary, and here is the boundary of the saliency map, where the saliency map changes or it goes too far, basically. And of course, the white regions are regions that we have not explored. So we don't know if there are other regions here. It's just a very under-approximate, rough kind of exploration. But with some heuristics, we had basically, we could find things that looked reasonable, at least. So here we can, basically we go as far away as possible until we find the boundary, and then we try to explore the boundary around it. And then we can continue, of course, we can go in other directions and keep exploring and so on. And this gives us an estimate, roughly, so we can say, well, definitely beyond this we cannot go with brightness, and we cannot go beyond this with the patch opacity. Maybe there are stricter requirements, but beyond this we are sure that we shouldn't go. And here we can say, okay, brightness, we can trust it up to roughly here. For the patch, it's kind of okay, possibly. We don't know what is there, but it's a bit like that. But even this, it actually doesn't really scale. I mean, I don't want to go into the details of the explanations or the experiments, but really we try different kind of combinations or different strategies for doing this, this kind of analysis. And the summary of this, without going into the details, it doesn't scale beyond neurons, like 10,000 neurons and so on. So it's we need something else. So there are some opportunities here for this community. We need some abstractions for sure. So instead of doing this exact analysis, even if partial, right, we need to leverage abstractions. This way we can cover the entire input space and we can do it faster. And then, on the other hand, we can also perhaps use this idea of robustness of explanations for other machine learning models. It's just some ideas, if any of you wants to pick them up. Any questions so far? Yeah?
So you're talking about the semantic information, right?
Sorry.
Okay, so we're talking a lot about like one specific type of explanation, right? Have you looked into any other like more abstract explanation, like for example, Lime, where they like make a linear representation?
Yeah. So no, this would be another option another way to go. Right?
Oh, okay.
This was one kind of explanation only. There are many others, and then yes, definitely you can try many others. There are also several perhaps more amenable explanation techniques, these logic-based explanations, maybe they are more fitting into this kind of context, but no, other things are also fine, yeah.
Thank you.
Okay, all good? Okay, then I can go to the rest of the talk. So basically here is state-on verification. And as I said a bit earlier, for these two parts, basically we use formal methods, but we don't do verification, we do something else. So for the explainability part, basically what we're going to do is basically use the abstractions. So we're going to abstract the models, but then without using, so we will not use the abstraction to do the verification, to verify, I don't know, classification, robustness, saliency map, robustness, whatever it is. But we're going to use this abstraction to explain what the model is doing. I'm using explainability, interpretability a bit interchangeably. I have to apologize for that. But yeah, in essence, explaining what models are doing. This is what I mean. And there's a bit of tension in machine learning between how the model performs and how easy it is to explain or interpret. So we have very easy models to explain, very easy models to understand, linear regression, decision trees, and so on. And then but they don't perform very well in practice unless the problem is small and constrained. And then we have this, well, I mean, I have to add other ones, but let's say all neural networks and, all the new other things, they're very accurate, they perform very well, but it's very hard to understand what they're doing. So for this part, I want to go, so the previous part was on neural network. To change, I want to talk about support vector machines here, just to see some other different model. So if you don't know what these are, they're basically planes, separating planes. So basically, we have this separation, well, we can call them curves, because when you have nonlinear SVMs, these are basically curves, but in essence, you're separating points in the space that are classified into different classifications. And these curves are supposed to, or these lines, are supposed to minimize the difference, or the distance, the margin is called, between the closest point in the space that are classified differently. And these are called the support vectors. So to give you an example, we have basically, let's say this line, we have 2 dimensions. These are the 2 support vectors. So this line here is our SVM. So this will basically separate all the points in this part of the space, will be classified as a circle, so -1. All the points in this part of the space will be classified as a triangle, so 1. What this is basically, we take the value of the classification times these are the weights that we learn during the training. And these are the support vectors, and this is the input vector, okay? So this is the SVM. You give it an input vector, it does these computations, and will tell you whether it's a circle or a triangle. And this is a linear SVM, so it's a very simple case that we can rewrite as a function as well, so as this line here, which is basically this function to which we apply the sine function to basically go on this side or on this side. So this is the example I will use for the rest of this part. Of course, we can do more complicated things, especially when the points in the input space cannot be linearly separated. In this case, typically what we do is we map them into a feature space, which is a higher dimensional space, but where we can find a way to separate them linearly. And the map from this to this is done through what is called the kernel function, and there are various kinds of kernel functions. There's these polynomial functions, radial basis functions, all kinds of things. We don't need to know the details about that, it's just know there's a mapping between the input space and this feature space that somehow works. So what I want to propose for this part, it's basically you have your input space, and you map, through this function, you map it to a higher dimensional space where you can find is a plane that separates the points. This is, the idea is, with these SVMs, you want to find these linear planes, but if you cannot find them, then you just go to a higher dimensions where you can finally find a linearly separating plane. Okay, so what I want to do is basically find explanations for SVMs. And so in machine learning, there's a category of explanations techniques that are called feature importance measures. So basically, these measure the contribution of the input features to the predictions. And there are tons of kinds of this. The most popular ones are these ones. And they have different flavors. So they can be local explanations, the global explanations. So local explanation, they explain one prediction. So you give it an input, and they explain why that input was classified in a particular way. Global means they explain the behavior of the model over the entire input space. Model specific really depends on the model on which that they are used to interpret. So they can be specific to SVMs or can be used for any other model. So these are the most common model agnostic explanations. And then there is another distinction, which is this performance or effect based. So the performance based, they basically decide the importance, they measure the importance of the features by checking, in essence, whether changes affect the performance of the model. So they need to know what are the correct, it depends on the data set, right? So, and they want to see how the accuracy of this model degrades with respect to the given data set, for instance, when we apply some changes. And the effect, so they need to know basically the true labels of the points on which they are tested. The effect base, they simply look at how the prediction changes, but they don't need to know whether the prediction is correct or incorrect. So what I'm proposing is another feature importance measure, but that we call abstract feature importance. It's specific to SVMs. We can use it for local or global predictions, explanations, and it's effect-based. So it doesn't depend on a data set. It really just looks at how the output changes with changes of the input. What else I wanted to say about this? Yes, the other thing that we wanted to do, to have something that was very fast to compute. Some of these techniques, some of this, like Lime or SHAP especially, they're very costly to compute, or PFI even, they're very expensive to compute, and we wanted something very, very fast. The question is then, why do we need another feature importance measures? There are various reasons, so I collected some. We don't need to read them. For like this most commonly used ones. The essence of it is that all these explanations, they make sense, but they are not grounded in any formal guarantees, right? So what we wanted really was something that it comes from an approximation that is correct by construction, done by abstract interpretation. We didn't want to depend from a data set or the accuracy of the model. We wanted to be extremely fast, as I said before, and we wanted to support both linear and nonlinear kernel functions, so linear and nonlinear SVMs. Because before this work, the explanation techniques that were available in the literatures for SVMs, they were all supporting linear SVMs only and not nonlinear ones. So the way we decided to do it is to use abstract interpretation, as I hinted already. Essentially, we have an abstraction of the input of the SVM, an abstraction of the computations of the SVM, and abstraction of the output. Then typically, what we do with this output abstraction is we use it for verification. And what we wanted to do here was to use it for explanations. So the kind of abstract domain that we used in this case was this reduced affine form abstraction. It's a sort of a zonotope abstraction with less terms. I'll show you what it means. So this is the SVM, or at least, well, let's say, okay, an SVM, what it does, it takes a vector of real numbers as input. It does the computation that gives a real number as output. It applies the sign function, and then it classifies into a circle or a triangle, let's say. This is for binary classification. We can do more, but yeah, the binary classification is a simple case. With the abstraction, we're going to use basically each input vector, each value in the input vector will be abstracted with this reduced affine form. I will show you what it is. So we're going to have a vector of the reduced affine forms. We're going to do the abstract computations with the SVM. We're going to get a reduced affine form as an abstraction of the output. And then we could do this verification thing, but we're not going to do that. We're going to stop here, basically. OK, so what are these reduced affine forms? They're basically linear expressions. So there is, in the linear expression, there's going to be this epsilon I terms. So each of these epsilon I terms will, in essence, represent the input dimensions. So here there are 2 dimensions, for instance. So we're going to have an epsilon term for x1, an epsilon term for x2. And then, so this is a linear expression, right? So we're going to have then an extra term, this epsilon r, that will accumulate essentially all the errors that we can perform, we can do with the nonlinear operations. Okay, and then it's an abstraction, so we also have top for anything that we don't know how to represent. I'll give you an example. This is the example from before, this line from there. So we have this SVM, this line here is this SVM. Then we typically apply the sign and do the classification, but we don't care, as I said. So let's say we want to know, basically abstract this SVM in this region of the input space, okay? So this is our set of input vectors. So the reduced affine form will give us this. So basically we have minus 0.5 epsilon 1. This will be basically abstracting this direction, so this side of the dimension, this box here. And then we have this other expression, 0.75 minus 0.25 epsilon 2 for this other part of the space. Okay, so together they represent this input space here. And then we do the computations of the SVM with this abstraction. So what it means is basically instead of the input vector, any input vector, we're going to have this, which represents several input vectors as input. And then we do the SVM computations as if it was just a vector of numbers, right? So we're going to have the weights are the same, the V1, this one, the support vectors are the same, so we just do the vector multiplication with the expressions here. And then we do the linear computations. And this gives us basically another expression down here that represents the output of the SVM, or abstracts the output of the SVM for all the inputs in this space. Then typically, I keep repeating this, but then typically you use this to then check if maybe the classification is robust, so you want to know if all these points are classified as circles, you can do that. But we really don't care about this. We want to stop here. So the question is, how can we use this abstraction to then decide which feature is more important in the input space or not? What we observed was that basically, well, since all these epsilon expressions here, they somehow relate to the input dimensions, then the coefficients can also give us an indication of the importance of those dimensions in computing the output, okay? The catch is that, depending on the precision of the abstraction, we may have a big extra term here that will catch a lot of information, so we'll somehow dilute the information that we have on the input dimensions. So if the abstraction is precise enough, then the coefficients here gives us a pretty accurate picture of the importance of the input dimensions. If it's not that accurate, if we have a lot of nonlinear operations, this term will grow and then will give us less accurate explanations. So we wanted to try this out, basically. So before I show you the experiments, the results, I can give you an example to make it a bit more concrete. So let's say we want to explain our SVM on the entire input space. The entire input space is represented as these two epsilon 1 and epsilon 2 terms. I don't have the time in the talk to tell you how this reduced affine form abstraction works, but basically there are rules on how you convert an interval into an expression of that form. So it's a very standard thing to do. We do the operations of the SVM in the abstract version, and what we get is this expression here. So we have 0.5 epsilon 1 minus 1 epsilon 2, and what this tells us, if you look at the coefficients in absolute value, is that this epsilon 2, so x2, is twice as important than epsilon 1, so then x1 then. And if you look even further, if you look at the SVM written in primal form, so as a linear expression, you see that these coefficients actually match exactly the coefficients that we get in that linear expression. And this is because it's an easy case. It's a linear SVM. Of course, when you have nonlinear SVMs, there is no match. We don't have a primal form, but there is no direct relationship. But in the experiments, we saw that this was an pretty accurate measure of the importance of the features, except when the abstraction was not precise enough. So to give you an idea, I still have a bit of time, okay. To give you an idea, we had considered different SVMs trained on this German data set. Just as an example, we took as a baseline, basically what we did was sampling randomly in the input space, perturbing the feature, and seeing how the result changed. So we had a very basic baseline, and then we compared our importance measure with the permutation feature importance, because we could just call a library to use it, and it was very easy to do. So what we did was basically compute these grades for the features. So basically we associated a grade of importance to all the features. Sometimes when we couldn't necessarily distinguish, so we can distinguish, if we want to be very fine, we can distinguish between different features, but we decided to group them based on if they had a very similar importance, we decided to group them. So basically these are the first 3 features are the least important ones. These 2 are a bit more important, and so on. And then what we did was comparing with the Euclidean distance between basically our grades and the grades of the baseline and the grades of permutation feature importance. So permutation feature importance, what it does is it takes, for each features, it does a perturbation of the data set, of the row, of the values in the specific feature row, feature column of the data set, and sees how the accuracy of the model degrades given that data set with the shuffled rows in that column. And based on that, it decides whether the more it degrades, the more important the feature is, and vice versa. So then we computed the distances from our measure, our grades, and the grades of PFI to the baseline, and also checked how long it took to do the things. And in all cases, you see that we are always closer to the baseline. But the grades, so for instance, here for the polynomial SVMs, you see that the abstraction is not great. So we don't quite match the grades of the baseline. We do identify the most important feature and one of the slightly less important ones. But beyond that, we do a bit whatever. But PFI does worse. So for PFI, this is the most important feature, which is the least important one for the baseline. So even if the abstraction is not that precise, we are still closer to the baseline than this PFI. And we do much better for the other SVMs. So the linear case, obviously, because it's really essentially one-to-one match with the linear SVMs, and still good with the radial basis form SVMs. And this was for one data set. Of course, we tried with different parameters for the baseline, number of sample nodes, how far we go with the perturbation of the nodes, and different data sets. And in all cases, we are still better, closer to the baseline, even for the less precise abstractions. So interesting opportunities to work there on abstract domains, if you want, really are on these polynomial SVMs. The abstractions there are not good enough, so there is more work that can be done to make it better. And then we also compare to Lime as an interesting, so this was for the local explanations. So what we did, since Lime uses a different way to compute the local neighborhood of a point, we compared with basically the way Lime works and our local explanations to a different size of neighborhood, so different size of an epsilon ball around the point. So this is a very small, slightly larger, and up to the global, so basically using AFI on the entire input space. And we compare the distance between our grades, our importance measures, and what Lime was computing. And in most cases, in fact, we were closer to Lime when we were explaining the entire input space rather than the local explanations. So we found this curious. We don't know exactly why that is the case. But yeah, there is certainly a mismatch. So either we are wrong or they are wrong, or who knows. In this direction, we also have a bit of an ongoing research on this sort of abstract explanations. So other kind of explanations that are somewhat logic-based. So essentially, finding the minimal set of features that can ensure the classification outcome or change it if they are modified for various kinds of classifiers. And here, what is interesting for this is that maybe we can use abstractions to do to find this kind of explanations. This similar kind of abstractions as the one that I show you can also gives us different kind of explanations of this kind. Okay, for the last bit on training, this is shorter, so don't worry. So yeah, I talked a lot about the deployment phase, so I wanted to touch a bit on the model training phase. So here, a lot of the work is done on the machine learning community, of course, and a lot of the work it still tries to address this adversarial examples problem. So the idea is they try to use training to make the neural networks, so the models, more robust. So in particular, well, they want to find parameters of the models, the weights of the neural network, for instance, that minimize what is called the worst case loss, so the maximum error that the network can make in a neighborhood of a point. So basically you have the points that they use for training, and you want to minimize the errors, so when the network is wrong. So you want to find the parameters that make these mistakes smaller in that neighborhood for each point, basically. So what that means is basically you try to make the network more robust by construction, so finding the parameters that try to make the classification more robust. But the problem is that this worst case loss here is very expensive to compute. In practice, nobody does that. But in the machine learning community, what they do is they use a lower bound to this, which is basically using quick ways to finding adversarial examples to points and adding them to the training set, augmenting the training set with those. Of course, we don't get any guarantees, right? So the machine learning, the formal methods community decided to then instead use an upper bound on that. So say, okay, we use, so we modify the loss that we use for training to use an upper bound. So for each point in the training set, we're gonna train it using an upper bound on this worst case loss. What is the problem with that? In practice, this certified training thing here, well, in theory it gives guarantees. In practice, it's pretty bad, because in practice, what you get, this is a comparison between the state-of-the-art in machine learning, state-of-the-art in formal methods. So this is the best current techniques for doing certified training. This is the best techniques for adversarial training. And this is the measure of how well these models resist to adversarial attacks. For certified training, you get some certified accuracy, but the empirical accuracy, how well they resist to adversarial attacks, is very bad. The best techniques in machine learning, they get to some 70% against very strong attacks. Here, what they get, even against very weak attacks, is 35%. So it's a big gap, more than 35% gap. So it's not interesting for the machine learning community. Also because when you look at the standard accuracy of these models, here you get 52%, where here you still get a pretty good accuracy of 93%. So in practice, any model that you train with certified training is useless for the machine learning community. So what some people have been doing is doing some sort of hybrid training. So essentially using a combination of adversarial training and certified training, maybe linear combinations or other kind of combinations. So basically during training you can tune how important is the certified training component and how important is the adversarial training component. And you can adjust this during training, you can adjust your training schedule, you can do all tons of things. But this in practice can work pretty well. So we haven't, at the time we had not formalized this way, but we understood later what we were doing. So I want to give you a bit of a, so we did some hybrid training and we did it on this random forest. We realized later what we were doing, but So random forests are basically sets of decision trees. So you have a bunch of decision trees and then you have a voting mechanism to decide the final classification. Voting mechanism can be majority or average or whatever it is. Okay, I will not say more than that. They're very simple models in themselves. They become a bit more complicated when you make them into a forest. So what we did back then was we considered fairness, so individual fairness, which is as a variant of local robustness. So what we wanted was to make some sort of certified training technique that improved the fairness of these models. But we did it in this hybrid fashion. So we basically used some training technique where we are also using adversarial training in some ways. And what gave us was basically models that were not degrading the accuracy that much, but were gaining a lot in this certified robustness, if you want, so certified fairness. The other thing that we did, that machine learning people liked a lot, was basically during training with a regular random forest, you basically have to tune a lot of the parameters. Here, the training process that we had designed was done in such a way that all these parameters were somehow inferred automatically during the training. So what we did was, yes, one other interesting bit was the size of the trees that we would get. They were actually much smaller than the ones that we would get with regular training. So what we thought was, why don't we get the parameters that we inferred with this training process and use them to tune the regular training of decision trees or random forests. So we did that, and as a result, we got something in between. So we got something with the regular training, but just with these hints from this certified training or hybrid training process. We got something with a very small decline in accuracy, but a big improvement, like 20%, almost 20% jump in robustness. And the size of these models was also much more contained, so easier to understand what they were doing. And this was actually very much appreciated back then. So it was an interesting way of using formal methods to do something useful for the machine learning community. And then we have a new results in the space. Last bit, I promise, I'm almost done. Basically, we did use the hybrid training, now that we understand what hybrid training is. And we used it to do adversarial training. So one of the problems in adversarial training is that it can be very costly as well, especially when you start doing PGD10 or this kind of things. So there is a branch of the machine learning community or the adversarial training community that uses this one-step attacks to mitigate this cost with good trade-offs. And what we did was basically show that in certain conditions, we can use hybrid training to get better empirical robustness than plain adversarial training at a smaller training cost. So we can do better than PGD5 in some cases at a smaller training cost. We're not yet as good as PGD10, but so it was a good example of how formal methods can be useful to machine learning in some ways. Okay, so with that, I think I concluded my overview of things that we can do. Of course, I hope maybe I gave you some ideas of things where you can, directions that you can look into. And I'm happy to take more questions. Thank you.
So thank you, Caterina, for the very interesting talk, as usual. Are there questions?
So thanks for a very interesting talk. Yes. What do you think will be the best way to communicate with the machine learning community? So will publishing formal methods paper in machine learning conference be enough, or should we need more general or deep kind of communication to integrate them? What's your experience about that?
So publishing is hard. Just publishing is very hard. So what I found useful is actually hiring a postdoc that comes from the machine learning community that is more open-minded than others. But it was a very fruitful collaboration. I learned a lot about their world, and in the discussions we understand that we speak different languages. Little by little, I don't know. Eventually, I think maybe workshops would be nice, but I think we need to gather a mass of people that want to talk to each other first. Yeah, it's not easy yet.
Thank you.
Yeah.
Other questions?
I just want to follow up previous question. Like, do you know why that so hard for the machine learning community? Is that the reason they don't care about the correctness at all, or it's just?
Yeah, so there is a part of that. So in a lot of their problems, adversarial training is good enough, right? That they have all this heuristics to measure the quality of their models, and for them is good enough. They don't work. They don't come from the same community, right? So they don't have the safety critical issues to worry about. We come from we have a different mindset, so we're all worried about using these things in safety critical situations. They are much less concerned about that. And also, yeah, it's also a problem of the language that we speak. So we care about this even complex properties. So in my tutorial the other day, I was talking about hyper properties of neural networks and so on. They don't care at all. Like for them, this adversarial example is the biggest problem that they have, and this is where the whole community is doing research on. Other properties, they really don't even care or consider that
until the huge problems came out after.
Yeah. But for now, it's a bit like that.
I really liked your introduction of AFI. Have you published or put a preprint or anything explaining it?
Yeah. So this one is in VMK 2024.
Okay.
I don't know if it's extremely well written.
Okay.
But yeah, this is where it was published, the work. Yeah.
Okay, I'll look into it. Thank you.
Okay, thanks.
Any other question?
Well, if not, thank you. You've been a very nice audience.
Thank you. Thank you, Caterina, again.